Okay, let's go hard one today, but I'm feeling pretty awake still, so hopefully I can do this within some sort of time frame that's reasonable. Find all people with secret hard. You're given an integer n indicating that there are n people numbered 0 to n minus 1. You're also given a 2D array meetings, where meetings of I has basically three values, x, y, and time. Indicates person X, person Y have a meeting at time. A person may attend multiple meetings at the same time. They really. Finally, you're given an integer first person. Person 0 has a secret and initially shares the secret with the person first person at time 0. Okay, so first person is going to be something that's not that's like 1 to n minus 1. Because person 0 has a secret. But anyways, this secret is then shared every time a meeting takes place with a person that has the secret. More formally, for every meeting, if a person X has the secret at time, then they will share the secret with person Y and vice versa. Secrets are shared instantaneously, that is, a person may receive the secret and share it with people in other meetings within the same time frame. Okay, so like if at time 30 person X has meetings with Y and Z and has the secret, then they can share it with Y and Z. And I guess also that means that Y and Z can share it instantaneously with other people that they have at that time too. Okay, return a list of all people that have the secrets after all the meetings have taken place. You may return the answer in any order. All the people that have the secret after all the meetings have taken place. Okay, so just infinite time. Or not infinite time, I guess time, the largest meeting time, maybe. Okay, I think first person is between 1 and n minus 1. Okay, yeah. N is 6, so there's 6 people. So you're just returning a list. I think maybe this is probably easiest to deal with sets here and then convert the set into a list here. First person have the secret is the first person that gets shared the secret from 0 is 1. So both 0 and 1 can spread the secret. Okay. I mean, doesn't seem particularly. Maybe it's just the compilation and how to do this efficiently. Okay, this is probably going to be O of n or O of n log n time. I'm going to make a slight guess that this can be O of n log n. Anyways, so 1, 2, 5 means 1 and 2 are in a meeting at time 5, 2 and 3 are meeting at time 8, 1, 5 are in a meeting at time 10. So here, since 1 has the secret, it can be shared with 2, so 2 knows the secret at time 5. And then 2 can share the secret with 3 at time 8. 1 can share the secret with 5 at time 10. So at the end of it all, 1, 2, 3, 8, 5, 10, and no, sorry, 1, 2, 3, 5 in addition to 0. So I think the reason why this would be n log n is I think you need to sort by meeting time. After you sort by meeting time, it should probably be a linear processing of the meetings in some fashion. Okay, so let's go ahead and do the sort here, I think. meetings dot sort based on the meeting time key or meeting time element within the array at that index. So I'm going to say key equals lambda I'll use, instead of x, I'll use meet as the variable name, where meet is going to be based on, so meet is the element within the meetings, so it's going to be one of those arrays. So it's going to need to sort by the time element, which is meet at meet at 2. And let's go ahead and print that. I guess maybe I don't need parentheses if I'm not actually forming a tuple. Print the meetings. Return just empty. I think this is how you would sort it. Yeah, so sorting by the meeting time here. Sorted by the meeting time there. Meeting times there, okay. Now, probably should look at the actual examples to see if there's anything tricky here. So 0 and 3 have the secret at time 0. So 3 shares it with 1 time 3. Sorry. This comes first, and neither 1 or 2 has the secret, so this thing doesn't do anything. And then at time 3, 3 shares it with 1. And also at time 3, 0 shares with 3, so 0, 1, 3. Okay. So 0 and 1 have the secret at the start. At time 1, I see. The trick is processing. It's the processing of the simultaneous times. So if you sort it and somehow you process this thing first, then you'd think to yourself that 2 and 3 would never learn the secret time 1. Technically, 1 shares the secret 2 with time 1, and then at the same time 2 shares the secret 3 time 1. So 1, 2, 3 have the secret, and then 3 shares it with 4 time 2, so everyone has the secret 0, 4. Okay. So the key thing is how do you do the simultaneous meetings and sharing propagation? So what I'm thinking might be used is for every, so key difficulty or kind of concern is how to share secret amongst participants. Participants in different meetings at the same time. How to propagate secret through that chain. So I mean, I'm visualizing making a graph in some fashion or some sort of connection between people who have for a particular time. So for a particular time, need to create some graph or connection between people in meetings. So if 1 has a meeting with 2 and 1 has a meeting with 3, and then 3 has a meeting with 4, all at the same time, then technically it all connects, and any secret known to any of them at that time would spread. Any secret known to any member of a connected graph would spread to everyone in that graph. Graph for every single time frame. I guess I could do that. It'd probably be all of the number of connections, the number of meetings in that block. I don't think it'd need to be of quadratic. But then you need to add in whether or not any of the members of the graph knows the secret. Ugh. You add in any of the members knows the secret, and that check to see if any of the members who knows the secret are part of the graph. That doesn't seem linear right now. That seems like an n times n comparison to quadratic. I wonder. I mean, as I build, yeah, so there could be multiple graphs at a particular time as well, right? So it could be that at time 10, like 1 is connected to 2 and 2 is connected to 3, so that's like a 1, 2, 3 connected graph, but then, or like a set, I guess, connected set. Then there's like maybe another one that's 5 connected to 6, 6 connected to 7. So then there's like a second pool of 5, 6, 7. 5, 6, 7. Oh. It would be pretty simple for me to go through all the meeting times and get an overall pool of everyone that is in a meeting at that time. And then maybe I drop in another bucket when I do it. I take people out of that pool and then drop them into another bucket. Nah, that works. Like if I look at, let's say at time 10, there's like a pool of people meeting that is, let's say 1, 2, 3, 4, 5, 6, 7, and then I see that 1 and 2 are in a meeting, so I have a set for that, and then I see that 5 and 6 are in a meeting, and maybe 6 and 7 are in a meeting. Then I see lastly that 1 is connected to 5. 1's connected to 5, then these pools need to merge. And then I have to do some sort of end process to merge it. Move end process to merge it. I assume meetings are unique, but I'm not. I guess so. There's nothing here that indicates that meetings are non-duplicate, possibly. I'm not sure if that makes a difference though. I mean, I wonder if I should. I could sort by both the meeting time and maybe some form of a smaller person, a smaller numbered person in the meeting. That helped me make a determination on who is connected to who. Like 1, 2, 5, and then if there's another meeting with 1, that has to be directly after it or within the chain of things that are after it. But also have a 1 at the start. And if it's not, then if you have a 1, let's say you have 1, 5, 5. So you have 1 meets with 5 at time 5, and then you have 2, 3, 5, 2, 5, 5. 2 meets with 3, and 2 meets with 5. So you don't actually have the connection between, you're not guaranteed that there's a consecutive connection between meetings or like people that are in, there's no guarantee that a person meeting multiple times at that time is consecutive within that ordered list, has meetings that are consecutive within that ordered list. Hmm. One, two, 5. Really need to make a graph. 1 connects to 2, 2 connects to 1, 3 connects to 4, 4 connects to 3. Do I make a set that, do I make a set? Interesting. 1 connects to this set, 2 connects to the same set, 5 connects to this set, 6 connects to the same set. Then if you have a linkage between two things that are already connected to sets themselves, then what you do? You would need to relink the sets. You need to combine them and relink the sets. And the sets themselves would need to link to a boolean whether or not any element within the set would link to a boolean for any element within the set. Knows the secret. Yeah, that's not good. Or I don't think that's fast enough. Like the set could be very large. There could be a lot of people in the 1 to 2. Propagating secrets. One to 2. Could I rewrite 2 and say 2 becomes 1? I don't know if that makes sense because I still need to know the unique ID. Oh. No. Can't do a single pass. Can't do a single pass. So the main thing is this thing right here. No, sorry, it's this thing. 1, 2, 1, 2, 3, 1. So if you process 2, 3 before you process the 1, 2. So if you process the 2, 3, could you somehow process it twice, guaranteeing that by the second time you process it that you've seen all the possible connections? 1, 2, 2, 3. So how big is this? 10 to the 5th. N is up to, yeah, that's a lot of people. 10 to the 5th size. 1, 2, 2, 3. So if I see 2 people that don't have a meeting or don't have the secret meet at a certain time, this would only work to eliminate them from sharing the secret at that time if neither of them have additional meetings during this time. But if they do have additional meetings, then I need to process those things first before I can fully determine whether or not this does in fact share no secret during that meeting. So 2 needs to, well, 3 is fine because 3 doesn't have any other meetings at time 1. But then 2 meets with 1. I mean, I could keep a tracker, a counter for the number of meetings I've processed with this person at this time. And if it's not equal to the number of people, then I add a second process. So I'm dealing with a deck, double-ended queue. I'm dealing with a queue where I process it once and then I add a second process for it. That work? I don't think so, unless I order it correctly. So I need to do 2, 3, see that there's another processing of 2 that needs to take place before I can say for sure that 2 doesn't have the secret. So then eventually I do the 1, 2, share the secret there, and then 2, 3 needs to get processed. The final determination of whether or not 2 interesting. So could I just make a graph? Maybe I just do need to make a graph at each time. Ugh, that seems so disgusting. Okay. Okay, so let's go. What's the term for a secret holder? Synonym for someone who knows a secret. A keeper. Trustee. Insider. I'll say keeper. Secret keeper. This will be a set with 0 and first person. I think that's a set. Print 0 and keeper. This should be true. Okay, yeah. So this would be the set of people who know secret. So for every time So let's say for I guess I probably want to do index. No, I probably want to do time, right? And index as well. Index being for the meetings index. So for, and I guess n is the number of meetings. So while index is less than n, I guess I pull the current time actually. Current time is going to be meeting set, this index, and then create graph of connected people at in meetings at this time. There might be more than one graphs of connected folks. So I think I need to start by doing graph, which is going to be default dictionary of list, where the key to the graph is going to be the person, the ID, and the value is going to be the list of people in meetings with, let's say this is an ID, list of people in meetings with ID. I guess we'll set people meetings with ID. Okay. So I need to iterate over every meetings that has this time. So while index is less than n and meetings at this index, oh, whoops, this is a tuple, or this is a 3-value array, so it has to be time is the third element. And while meetings at this index is equal to this time, I'll go ahead and pull that x, y, and time, which I already know. Meetings at this index. Eventually I need to do index plus equals 1 before I forget, because it's not a for loop. Graph at x is equal, appends this y. Graph at y appends this x. I think that should form it. I think maybe I'll need to have a set of current users. So this group is going to be a set. I'm going to add everything to this set here. Group dot add x, group dot add y. I guess maybe I could pull the key of the graph, use that as set. How fast is for the set of keys from the graph from a default dictionary? It's probably easier to just deal with the group, my own data structure for keeping track of the users. I also need to know I probably need something like a visited, which is also default dictionary of integers for the key is the ID and the value is equal to the number of checks on ID, which is going to cap out to the number of relationships that ID has. So the number of meetings that ID is in, and if I've visited, if a person has been visited every time that they've had a meeting at this time, and they haven't learned the secret by then I think it's is that when you would that when you would actually verify that there's no Interesting. You know what? I think maybe I build the graph and I start by actually, so this is I'll say this is actually starters. So for everyone in the group, I don't think I need group actually. I think I need something like everyone that has this secret at this time is a starter. So if X is in people that have the secret, then X is going to start sharing the secret. If Y is in a group that has the secret, Y will actually start as well. Yeah, okay. And then here, after I've made the graph, then I need to share. So for every start, I guess this should be plural. Or maybe this should be shares. I'll say starters. Every starter and starters. Then what they're going to do is they're going to shucks, should this should be a queue or a stack. Because I need to push things onto it. Yeah, this should be a list or maybe a queue. So maybe I need to convert starters into a list. Starters. Let's get a list or a deck. Because I push. I pop off one, connects it to pop two off, push the connections of two onto the stack, 4 kicks. Okay, I think maybe it should be a set and a queue. So could be a queue or could be just a stack. Process stack. I don't know if this really makes a difference. Starters. Okay. Maybe I should have it be called done. Maybe it should be called shared. They've already shared the secret, or they've already have the secret shared to them. It's kind of funny that I'm just relabeling it even without changing the code. But logically it's different in my mind. Yeah. Shared is almost like a done set. So the process needs to start with those that have been shared within this time frame. At the start anyways. Okay. So, and then I need to just while process. So while there are people to process, then I'm going to go and have, let's say, is ID a keyword? No, it's a function. Okay. I don't want to use keywords or built-in functions. Let's say I'll call this a share. It is going to be process.pop. And then I'm going to go through the list of neighbors to share. So for each neighbor, or I guess each, what do I call someone that's meeting with them? For each meter, someone who meets. For each, I guess other, I'll call it other. So the other person in the meeting room in graph of share. If the other is already in shared, then continue. Otherwise, other is going to be added to shared, and then I'll do process dot append other, and also the people that keep it. I guess this should be keepers. I guess this should be, yeah, keepers. Keepers of the secret, keepers of the secret. Keepers.add share, add other. Oh my god, this is not how to do it. Oh. This is shared.add other. Shared.add other. Shared is this set. Keeper.add other. Process.append other. Yeah, I think this is good. This is good. And then it would move on to process this other, do the connections with that person. Is that right? this might be incorrect. Others and shared. So so just going through everyone that has a secret. When the next person that has a secret gets processed. Yeah, I think this is right. Okay. And then I just return at the end the list of people that have it, the list of keepers. Okay. Well, let's see if it gets more complicated test cases. Sure, there's some mistake. Oh. Interesting. Alright. I mean, it was a hard. I'm not sure if I really want to improve this. It seems pretty I think this is pretty compact. Or I don't see any obvious places where I want to improve this or want to try to find a more efficient method of doing this. Sometimes you kind of have a sense of spots where it could be improved, and it's kind of like whether or not you want to kind of make that jump. But here, this is all feels pretty good in the sense that I don't, yeah. Huh. So did I ever make use of time being 0? I don't think so. I think I just need to have index. This seems a little bad to have index less than n for both these things. Could I make a dummy meeting somehow? I don't think I can make a dummy meeting. Could I make a while true loop? Really don't like having a while outside loop with a while inside loop that has the same conditions. So I could do while true here, while index less than n here, but then I would just need another if statement, which is going to be equivalent, where the if statement breaks when index is n. While index less than n. I can do while meetings is equal to this time, and while time is not infinity, and have an extra meeting added to the array. So for instance, I could do something like meetings.append a dummy infinity time, and let's say -1, -1, no valid. Oops, what's the other? That's the wrong ordering. Infinite time while I can do while true here. Time is this thing. while time doesn't equal infinity. While time doesn't equal infinity. I get the current time, and then here this can be while meetings equals this current time. And then it does actually do yeah, it's not gonna work. This is too complicated. It's lost in the sauce if I try to do this. Okay, anyways. Make the connective graph. I think this is extremely concise version of how to make a graph. Could make it based on like an indexed array, an array of lists maybe. An array of lists. Shared. For every meeting at this time, form the graph. If X is in keepers, add it to the shared. If Y is in keepers, add to the shared. Index plus equals 1. I think maybe what could be shortened here is keeping track of the people that don't know the secret. So people that don't know the secret could be called maybe outsiders. This will be the count of people who don't know the secret. And here this will be if this thing else outsiders plus equals 1. Actually, it could be just false, right? Because I really don't care about the count. I just care about if there are outsiders. So initially this is going to be false. If there are folks who don't know the secret at this time. So here outsiders becomes true, else outsiders becomes true. And then I can skip all this. If outsiders is equal to false, then just continue. Rather than try to process a bunch of stuff that doesn't lead to anything. Because there's no one that doesn't know the secret. I wonder if that speeds it up. Okay, I mean, it gets me over the hump in this distribution. Graph y appends x, x appends y. If x is in keepers, they don't like the syntax. Looks really funky. If x is in keepers, if y is in keepers, index increments. Otherwise, do the processing. Convert to a list, do the processing. Yeah, I think it's fine. I think it's good. Alright, so summary here, this is going to be main issue is sharing the secret to everyone who is connected through meetings at a given time. This is a version of dealing with connected graphs. Need to form a graph for those meetings. Connected, or the nodes are basically people, person, and the edges indicates a meeting exists at that time between those people, those two people. Any person, any node that originally has the secret spreads that secret to all nodes in the connected graph. And when dealing, so those main steps would be 1, sort meetings array by meeting time. 2, for each meeting time, create graph connected nodes people at that time. This is typically done with a default dictionary of lists, where the key is the person, the list is their connected people, or 2D array, I guess. An array of, I guess an array of list, where the index is the person, and the element at that entry in the list is an array, or the element within that array is a list. Anyways. 3, yeah, 3 is going to be, actually this is for each time. This is going to be, part A is going to be this, part B would be keep track of every node that already knows the secret. This is going to be with a set. This is going to be starters of spreading secret to other nodes at that time. And then C, convert the set to a list, basically a process stack, and process each node in the stack, where within the processing of this, we're processing the node will do 1 pop from stack to iterate over the neighbors or the other folks in meetings with them, and then add them to secret and stack if necessary. And then again, after all that, it's going to be return the set of people who have the secret converted to list. Right, so you have your initial sorting, you have your initial set of people that have it, all these keepers. You have your iteration, which goes over the times, and for any given time you want to figure out all the people that are connected in meetings at that time. So you have your graph, which is a default dictionary, or I use a default dictionary list, and then while I'm at an index that matches this time, then I'm going to build the graph. So I do graph at x equals, or appends y to the list at that entry. Graph at y appends x. I do a small optimization in that I keep track of a shared, so the people that are going to share the secret this time, if they already know the secret. But I also do a boolean for if they're to track if there's anyone who actually doesn't know the secret in a meeting at this time. Because if everyone who knows the secret if everyone in meetings at this time already knows the secret, then I don't need to process anything. Like everyone knows the secret. Because the processing does take a non-trivial amount of things if there's people who have it to share. So anyways, after that, convert the shared list into a process stack. And then process the stack using kind of the normal stack processing algorithm. Pop from the stack, iterate over the other people in meetings with that share. If they've already shared it, then ignore. Otherwise, add them to the shared group, add them to the keepers group, or shared set, keeper set, and process this other person that has yet to share their secret. Alright, time complexities can be O of n log n to sort the meetings, and O of n is the length of meetings and n is also the number of users. I think it's O of n to share the secret. At a given time. But then there could be n times. Overall, I feel like it should be linear, but it should be capped based on the number of meetings. Yeah, I'm not quite sure about this. Actually, unsure. Because the outer loop of this thing is based on the time, and then the inner loop is based on the number of users at that time. So in theory, it might be like O of square root of n squared. Ugh, I don't know. It doesn't feel like it's n squared. I mean, it definitely is n squared. It could be n log n. I don't know. So, but I think overall, pretty sure this is the slow function here is the sorting function. So place complexities can be O of n to keep the default dictionary of lists for the connected graph.